Welcome to the Enhancement for Forecasters course titled Satellite Applications for Tropical Cyclones, Dvorak Technique. The instructor for today is Ray Zare.
This is a quote from a recent article in the Bulletin of the American Meteorological Society entitled The Dvorak Tropical Cyclone Intensity Estimation Technique, a satellite-based method that has endured for over 30 years. In the United States, when hurricanes are threatening the coastline, there's almost continuous aircraft reconnaissance flights into the hurricanes to observe their position intensity. However, in the rest of the world, the primary tool used for hurricane tracking and intensity is the analysis of satellite images. It's probably a good idea to say a few words about terminology before we get started, just so there's no confusion. Different terms are used for the same thing in different parts of the world. For example, hurricane, typhoon, and cyclone. Tropical depressions and tropical storms are used for wind speeds less than hurricane force, as shown here. A storm name is often used when tropical storm intensity is reached. It is often useful to use the generic term tropical cyclone to refer to all intensities and all locations. This practice is also used for this training session. Another classification you've probably heard of is the Saffir-Simpson category. With this classification, there are 5 categories based on wind speed for intensities greater than hurricane intensity. For example, a Category 3 hurricane is for wind speeds of 96 to 113 knots. What's shown on this slide is generalized and applicable to most locations. There are, however, some variations from what's shown on here that's used in some regions. For example, India and Australia use slightly different terminology, but the basic term tropical cyclone is used in those regions as well. Also, I apologize for using non-standard units of knots for wind speeds. However, many operational centers still use this unit, so we're also going to use it in this training session. Just as a reminder, a knot is a nautical mile per hour. 1 degree latitude equals 60 nautical miles, 70 statute miles, and 111 kilometers. So conversion factor of knots to miles per hour is 1.15, so that 100 knots is 115 miles per hour. Another useful approximation is that knots are about a factor of 2 different than the standard metric unit of meters per second. So 10 knots equals 5 meters per second. It's important to point out how the Dvorak technique works in general. As a tropical cyclone intensifies, the winds increase in response to the pressure gradient getting stronger due to the central pressure decreasing. In response to those changes, the cloud patterns change. The cloud patterns are those that are viewed by satellite images in both the visible and the cloud temperature images as detected by infrared satellite sensors. The Dvorak technique has its own intensity units called T-numbers. They can be directly converted to a maximum surface wind speed or a minimum sea level pressure, also known as central pressure. Note that 1 T-number represents 1 day's intensity change at an average rate. The pressure associated with the Dvorak intensity is different in different regions. This is because the broad scale pressure may be different, and it's the pressure difference or gradient that drives the wind speed. However, the maximum wind speed associated with the T-number value is the same everywhere. This table gives wind speed associated with all T-numbers in 1/2 T-number increments, which are used for intensity assignments with the Dvorak technique. The table also shows central pressure assignments for Atlantic and Pacific. Here, Pacific refers to the western North Pacific. Note the differences. This is because pressure in general over a large area is lower in the western North Pacific. This slide shows 3 tropical cyclones with very different intensities and very different patterns. The Dvorak technique is based on the premise that tropical cyclones have characteristic evolutions of cloud patterns that correspond to stages of development and certain intensities. This slide shows images during the developing stages of two well-known hurricanes, top to bottom on the left, followed by top to bottom on the right. Note the changes that you see during intensification. We will be discussing those changes in detail because that's what the Dvorak technique is based on, pattern changes, not the size of the clouds or the amount of deep convection. It's the cloud patterns that matter. Here we see typical changes during weakening stages. Note the appearance of the images on the right. These are enhanced infrared images. While all the previous images we've looked at are visible images, infrared images, often referred to as IR images, are used to view clouds at night since it's too dark for visible viewing. IR images are comprised of infrared temperature measurements. In general, the higher the cloud, the colder its temperature. However, when clouds are thin, the IR temperature will be warmer than the actual because some of the radiation from warmer clouds or surface below will pass up through the cloud. So now we're going to discuss IR image enhancements. The IR images on the previous slide were enhanced with an enhancement known as the BD enhancement or BD curve. This is a specific enhancement that is used with the Dvorak technique. Back in the 1970s, many satellite images were transmitted by facsimile and black and white laser printers. There was no color capability, so only shades of gray and black and white could be used. In the cold range, the Dvorak BD enhancement uses 5 degrees Celsius intervals for discrete shades, as shown on this slide. Using color enhancements on IR images allows much greater capability to bring out the full information content of the IR image. This slide shows the enhancement colors used with an enhancement curve that will be used in this training session that employs colors and in the cold ranges has a different shade for each 1 degree Celsius. Dvorak's original formulation of the technique, which is still used, has a 10-step procedure shown here. The flow chart on the right is used by the analyst, and specific portions of this chart will be covered in this training. This 10-step procedure was needed originally to help assure that different analysts with limited number of available satellite images could still get reasonably consistent results. Some of the images in those days were rather poor quality. With more timely and very high quality images available today, good results can nearly always be obtained by assigning intensity according to the data T number. The Dvorak technique also has an important procedure for weakening tropical cyclones. A CI number, CI stands for current intensity, is assigned. This is because weakening cases, the CI may be higher than the T number. For developing and steady cases, T number and CI number are the same. This training session is focused on concepts and actual image-based measurements rather than the minute details of each step shown here. However, we will briefly cover the important issues of constraints to the final T number and how the final T number is adjusted to give the intensity for weakening cases. This training session will use the simplified approach as outlined in this slide. The basic concepts of the Dvorak technique will be covered with this simplified approach, and the focus will be on concepts and actual image-based measurements. Expanding a bit on the previous slide, the following are important things to note about the Dvorak technique. The center location is a very important part of the procedure. The pattern also must be determined before any measurements can be made. The measurements that we'll be making from the images will be as quantitative and objective as possible, but still will involve some subjective and qualitative evaluations. The T number and CI number are the same for intensifying and steady tropical cyclones. With weakening cases, the CI number may be higher than the T number. One aspect of the Dvorak technique that's important but sometimes overlooked is when do you start? This slide covers the guidelines used for initial classification, which starts with a T number of 1. First, you need a persistent tropical weather system, meaning that it lasts more than 12 hours. This tropical weather system has an associated cloud cluster comprised of deep convection. Second, you need to be able to identify a center that persists for more than 6 hours. And then there has to be a sufficient amount of active deep convection. This slide begins our discussion about the first step in the simplified approach. Locating the tropical cyclone center is also called fixing, and center locations may be called center fixes. In addition to being the first step of the Dvorak technique, the center locations are also valuable for other tropical cyclone procedures and an integral part of the tropical cyclone forecasting problem. This is an outline of all the concepts and methods that will be illustrated in this training session pertaining to center location. We will look at both single image procedures and procedures using animation. We'll also look at some additional image types that are very helpful for center location. As a point of clarification, the circulation center of interest is the one at the surface. Sometimes a mid-level or upper level circulation center exists that is displaced from the surface center. With a strong hurricane, the center is aligned vertically and is very deep through the entire depth of the troposphere. The surface circulation center, as defined by the surface winds, also in general corresponds to the lowest pressure. We will discuss different situations and approaches to locating the center. This depends on how the tropical cyclone appears in the image. These methods apply to a single image, which may be either visible or infrared. The methods are listed here, and we'll look at each of them. First, we'll show examples with an eye and also examples with central dense overcast, also called CDO. This image shows a well-defined circular eye with Hurricane Rita 2005. This case has a near average eye size for a very strong hurricane. With an eye like this, locating the center is very easy. It's at the center of the eye. The eye is the area that is clear of deep clouds, though there may often be shallow clouds close to the ground. The strongest winds are near the edge of the deep clouds surrounding the eye, called the eye wall. Here's the same image zoomed in. Note the shadows and the brightest clouds. The shadows and the brightness of the clouds tells you about the sun with respect to the hurricane and the viewing angle of the satellite. It gives a three-dimensional perspective. In this case, most of the eye is within the shadow of the tall eye wall cloud to its west. Here we have another image of Hurricane Rita just 3 hours later. It's now after dark, so we'll use IR images with color enhancements to indicate the IR temperatures. The eye in an IR image is the very warm spot surrounded by the very cold cloud top temperatures. The center, of course, again, as with visible images, is at the center of the eye. Back to the visible high-resolution image of Rita, you can actually see right down into the eye. However, there's a shadow and the sun is not shining directly down, so the view you get of the eye is dependent on the sun angle and the viewing angle of the satellite, and also how big the eye is. Here's the same image zoomed in even more. A special enhancement is used on this image so you can see the clouds right down near the surface inside the eye. Locating centers with well-defined eyes is simple and straightforward. Even so, center fixes like the one shown here may not always match up exactly with surface centers. This may be due to differences in Earth locating a point at cloud top versus a point directly beneath it at the surface. This is referred to as parallax. Corrections for this can be made, and for tropical cyclone center locations, these corrections are usually quite small and small enough to be ignored. With poorly defined or large ragged eyes, as shown here, there's a little more uncertainty in locating the center, but finding the approximate geometric center of the eye is the goal. Here's an example of what Hurricane Wilma looked like after it had crossed Florida and was moving rapidly to the northeast. We can toggle back and forth between this image and the matching IR image. Here's the same image zoomed in with high resolution visible. The location of where the aircraft located the center is denoted by the red hurricane symbol. This is an IR image of Tropical Storm Rita before it intensified into a hurricane. In this image we see what looks like an eye, but it's not really an eye located right here. However, it does lie within a break in the clouds near the center. In the next image, we've drawn a circle. In this case, the spiral shape of the deep clouds and the poorly defined circle of cold clouds surrounding the circulation center indicates a center location near the center of the white circle. The next image shows the location where the aircraft reconnaissance located the center at the time of this image. The following image is the BD enhancement of this image. This is an IR image of Rita on the previous day showing what is called a central dense overcast, or a CDO. The CDO is the persistent mass of deep cold clouds that cover the center before an eye is observed. It is often, but not always, circular in appearance. In general, the center is located at the CDO center. But there are also other things to look for to help locate the center. Note the tight gradient of IR cloud top temperatures on one side of the CDO. The center is usually closer to the edge with the tight gradient. Also note the curved band of cold clouds and where it merges with the CDO on the northeast side. Curved bands such as these will be in a spiral shape, spiraling about the center. Here's the same scene zoomed in with a visible image. This is the matching IR image. By enhancing the visible image as shown here, overshooting cloud tops and patterns can be seen at cloud top. These can also be used to help locate the center with the CDO. The blue hurricane symbol marks the location of the aircraft located center. Here's the same thing on an IR image with each of the enhancements we've discussed, and the aircraft located center is marked by the small hurricane symbol. This slide gives a review of locating centers with EYE and CDO patterns. Now we'll discuss how to locate the center for weaker intensities with shear and curved band patterns. The things we'll be looking for in the images to help locate the center are listed here. This is an example of a center located by the pattern of the low-level clouds. A center that you can see in the low-level clouds, which are displaced from the deep convective clouds, is often referred to as an exposed center. In this case, the center is located within the tightest curvature of the inside edge of the fishhook-shaped cloud. The matching infrared image is displayed here. Note if we toggle back and forth that the low-level clouds are much more difficult to see in the IR image, and this is because the cloud top temperatures of the low-level clouds are quite warm and do not have as much contrast with the ocean surface. By the way, this example is Tropical Storm Ophelia from 2005. Here's a close-up visible view of the same scene a few minutes later. This is an example of a case with which the low-level cloud lines and their curvature help locate the center within the deep clouds. The curvature of the clouds increase with closer distance to the center. The lines also converge toward the center. This image shows the tropical depression that later became Tropical Storm Emily in 2005. It was first designated as a tropical storm about 12 hours following the time of this image. This is Tropical Storm Emily the next day. Note that the dense, thick clouds have an axis that is spiral-shaped. The center is located near the focal point of the spiral. Using the spiral method, the center is located by the red hurricane symbol shown here. Here's another technique for locating the center. It's called the wedge method. The wedge refers to the incursion of warmer IR cloud tops into the curved band pattern of colder clouds. The procedure for getting a center location with the wedge method is as follows. First, locate the axis of the primary curved band. Then draw a straight line from the innermost end of this axis to the wedge. The center lies at the midpoint of this line. This image illustrates that procedure. A warm wedge intrudes into a spiral-shaped cloud mass. The cloud mass has one or more cold axes aligned along a spiral or comma shape. The yellow line shown here goes from where the spiral axis is located at the inner cold cloud edge, here, it then goes along the yellow line to the innermost incursion of the warm wedge. The tropical cyclone center is then located at the midpoint of this line, halfway between both ends. Here we show it with a pink hurricane symbol. By the way, this example is Katrina from 2005, near the time of its first designation as a tropical storm in the Bahamas. Here's what the visible image looks like with that case. A line can be drawn comparable to the IR image using the wedge method. That line is shown here as the red line, and the center is the center point of the red line. So far, we've been discussing how to locate the center with a single image. One can also take advantage of using animations or movies of satellite images. These are available from continuous viewing with geostationary satellites. The following guidelines can be used. Both the low-level cloud motions and the deep convective cloud motions rotate cyclonically and spiral in toward the center. Remember, cyclonic refers to counterclockwise motion around the center in the northern hemisphere and clockwise in the southern hemisphere. Anticyclonic, of course, is the opposite motion around the center. With this image, animation is particularly helpful in locating the center. It is difficult to tell from this image alone where the center is. This is the tropical disturbance that became Katrina. This is a few hours prior to its first classification as a depression. These disturbances are also called easterly waves. This is the matching visible image. With visible images, the low-level cloud motions are much easier to see. They're very important in locating the center. Also, the animation is very helpful in showing the motion of these low-level clouds. Here we'll toggle back and forth between the IR and the visible. Here's a movie of that example. Note how the motions help. So where's the center? Remember our guidelines. When looking for the center of a cyclonic circulation, primary indicator are the shallow, low-level cloud motions. Secondary indicator are the deep cumulonimbus cloud motions. You want to ignore the high-level cirrus motions. This is the same view with zoomed in rapid interval images. Try to locate the center with these images. Better resolution, both spatially and with shorter time interval between images, is very helpful. The center is located near the red hurricane symbol at the end of the movie loop based on the satellite cloud motions. This is a larger scale look at the same scene with the same location marked. Tropical depressions and pre-tropical depression easterly waves have more inherent uncertainty in the center location. This is because the centers are not as well defined. They usually have a more broad circulation than hurricanes or tropical storms do. The term broad circulation refers to the trait that the strongest winds are further away from the center. Here are two examples that have multiple centers that can be identified in the visible images. Francis and Jean. If a dominant center cannot be identified, it is useful to use a mean center position as a cyclone center. An average position of various centers may be used as the tropical cyclone center. This will approximate a broad center about which the multiple centers are moving. Another satellite data type that can be very helpful for center location, particularly at night because there's no visible images, are images at 3.9 micrometer wavelength. Sometimes this is called the near IR band. It lies between the visible and infrared image wavelengths. Images have characteristics of both visible and infrared. Here's a visible image of a Category 1 hurricane experiencing vertical wind shear from the west. This is Hurricane Bertha in 1996. Here's the matching infrared image. This is an IR image of Bertha a few hours later. It's now nighttime, so no visible images are available. The next image, shown here, is a 3.9 micrometer image. A special enhancement has been used with this image to better depict the low-level clouds and to distinguish them from the cold clouds. It is now nighttime, so no visible images are available. This is an IR image of Tropical Storm Lee from 2005. The center location is depicted by the low-level clouds is very difficult to see in the IR images. Using the 3.9 micrometer image with a good enhancement is much better. The center can clearly be seen in the low-level cloud field to the west of the deep clouds. We can toggle back and forth between the 3.9 and the IR image as shown here. This is a movie of that example. This is the 6-hour period centered on sunset time. With this combined image product, the nighttime 3.9 micrometer images are combined with the daytime visible to provide 24-hour coverage and give better continuity for viewing low-level cloud motions. This animation is the same product covering a large area of the tropical Atlantic and Central America. The terminator is defined as the sunset or sunrise location at the Earth's surface. It can be programmed accurately, and with this product is used to separate the visible image data from the 3.9 micrometer image data. Microwave images may also be useful for center location. The microwave images are available from polar orbiting satellites. They give views of cloud and rain patterns that are obscured by thick cirrus clouds in the eye are invisible. This is an 85 gigahertz microwave image. It shows active convection with large ice particles in the dark blue. Light green shades show liquid water clouds that are sometimes obscured by cirrus clouds in IR images. With this enhancement, land areas show up yellow, while warm, mostly clear ocean areas are dark blue. As you can see, this image is a mosaic of multiple orbital passes. This is an example of a microwave image that is very useful for center location. It shows a spiral pattern in the low-level clouds where the dark blue on the light blue background are the cloudy, rainy areas, suggesting a center location just north of the northernmost active deep convection enhanced in red. In the matching IR image on the left, the cirrus clouds are obscuring most of the low-level clouds near the center. This is Tropical Storm Boris in the eastern Pacific. Interpretation and application of microwave images is a very important topic in tropical cyclone analysis by itself and is not covered in this training session. In the next image, we see another microwave image product. This microwave image product is referred to as the color composite image. Note the mirror image appearance compared to the previous slide in the low-level cloud features. Interpretation of microwave images by themselves can be difficult, but when combined with the more familiar views, invisible and IR images as shown here, the additional information to help locate the center becomes clear. The previous example was just before sunrise, so no visible was available. This shows the same products about 2.5 hours later with a visible image in the upper right-hand corner. So that completes our discussion of locating centers. And you'll see shortly how the center location is an important component of intensity analysis using the Dvorak technique. The remainder of our training will address intensity estimates using the Dvorak technique. In recent years, other satellite data and procedures listed here have been developed to supplement Dvorak estimates and provide additional information. For operational final intensity estimates, in situ observations from ships, buoys, and surface stations, as well as aircraft observations, are of course very important. These data are also used for validation, development, and refinement of the satellite techniques and algorithms. This training will primarily cover the Dvorak technique. We will briefly discuss the objective Dvorak technique and advanced Dvorak technique. The AMSU algorithms, scatterometer winds, and cloud motion vectors will not be discussed. We will now discuss the important step of the Dvorak technique, which is to identify the pattern. The pattern will be one of 4 types. We have already introduced these patterns as features to use for center location, but now we're going to discuss them as an important step of the Dvorak technique. And we'll see how deciding on what pattern you have tells you what to look for to estimate the intensity. First, we'll just show examples of each pattern. This is the curved band pattern. The curved band pattern involves the deep convective cloud bands and their extent and curvature. This example is Tropical Storm Ivan from 1998. there's a single prominent curved band of deep convection. Here's another example. The curved band extends from east-northeast of the center, curving around to the north to the coastline, and then curving back to near the center. The center is just offshore, further down the coastline of Mexico. Now we'll look at examples of the shear pattern. This is another view of Bertha, which we looked at earlier. The shear pattern exists when there is a large asymmetry of the deep convective clouds with respect to the low-level center. With the shear pattern, the surface center is located by the low-level clouds outside the deep convection near its edge. Or it also may be within the deep convection, just beneath the edge. This is another example of a shear pattern, Tropical Storm Lee from 2005. This is an example of a CDO pattern. The CDO was defined and described earlier in our discussion. The central dense overcast is the persistent mass of deep cold clouds that covers the center before an eye is observed. It is often, but not always, circular in appearance. In general, the center is located at the CDO center. The Dvorak technique also refers to this as the embedded center pattern when doing analysis with enhanced IR images. Here's another CDO example. The CDO is the roughly circular mass of cloud immediately south of the eastern mark of the Dominican Republic. The eye pattern was defined and described earlier in our discussion and is usually very easy to identify. Many of you probably know that 2005 was a very active Atlantic hurricane season. This slide shows all of the 2005 Atlantic hurricanes that had well-defined eyes. Since each image had been remapped and are of the same scale, you can intercompare each of them and note the variety of sizes and shapes of the eye. The top row on this slide from left to right are Dennis, Emily, Katrina, Maria, and Nate. And the bottom row, Ophelia, Rita, Vince, Wilma, and Epsilon. This ends our discussion of the four basic patterns. Before covering the next step of the Dvorak analysis, here's a quick review of material from the introduction. We've covered center location and pattern identification. Next, we'll discuss what to look for to assign the T number. We also want to review what we mean by the term intensity. Intensity is defined as the strongest wind. For a tropical cyclone, it is a best estimate, given all available information, of the highest wind speed anywhere associated with the tropical cyclone. It is given in increments of 5 knots. The operational practice in the United States is to use 10 meters and 1 minute average as the standard surface wind. Since knots are not standard units, this slide has a reminder that a knot is a nautical mile per hour and some conversions. If one is making measurements with an airplane, or if a tropical cyclone passes directly over a barometer, minimum sea level pressure is a very useful measure of intensity, since it is an easier measurement to make than the highest wind speed anywhere. Also, central pressure changes are very closely related to wind speed changes. Now we'll continue our discussion of the Dvorak intensity analysis. So far we've covered center location and the 4 basic patterns, steps 1 and 2 on this slide. As mentioned earlier, this training uses this simplified approach, and we'll now discuss steps 3 and 4. In order to assign intensity using the Dvorak technique, one must determine the pattern. As shown here, choosing the pattern by itself identifies a range of intensities. The Dvorak technique then uses specific characteristics and measurements to assign an intensity to the nearest 1/2 T number within each range for each pattern. There are 4 basic patterns. Banding eye is also shown here. It is a subset of the eye pattern. The Dvorak intensity analysis can be simplified to the procedure shown here. Learning the basics of the Dvorak technique involves learning what to look for in the image and how to evaluate it or measure it. So what we're going to discuss for each of the patterns is, what do you measure in the image? We'll start with the curved band pattern. The spiral arc distance is what you evaluate or measure. There are 2 important points. Curved band refers to a deep convective continuous spiral band. And second important point, the same measurement is made with both visible and IR images. This slide illustrates how to measure the spiral arc distance. A spiral like the one shown on the left is overlaid on the image and aligned along the primary curved band. The spiral arc distance can be measured in units of tenths, and note that it can be greater than 1. Also, it should be pointed out that for this measurement, the center of the spiral does not necessarily coincide with the tropical cyclone center location. Also note on this slide, DT number is used. DT stands for data T number. In this training, I will sometimes use DT and T number interchangeably. To be technically correct, the data T number should be used when talking about making measurements and assigning values. But in practical use, most of the time, the final T number is the same as the data T number, so that's why I often use them interchangeably. Here are the T number assignments according to the spiral arc distance measurement. This chart is from Dvorak's original paper. And if measurements are made to the nearest tenth, one can use the labels that have been added here at the top of each figure. They give the same results. So as you can see here, using the curved band spiral arc distance, if the primary curved band spirals approximately halfway around the center, you have a T 2.5. If it is just slightly more than fully surrounds the center, you have a T 4.0. Here's an example to show Dvorak analysis for the curved band pattern. The curved band is defined by the axis of the brightest clouds. That is, the most dense, deep convective clouds. Here, a log 10 spiral with markings at 1/10 interval are overlaid on the image. The spiral is aligned approximately along the central axis of the curved band, and this puts the spiral center near the tropical cyclone center. The spiral arc distance in this case is 0.7. So with Tropical Storm Ivan example, the 0.7 spiral arc distance gives a T 3.0 and a maximum wind of 45 knots. Here are the matching IR images. The same procedure is used for curved band T numbers with IR images. The coldest temperatures are aligned along the curved band and used to define the curved band axis. The T-number analysis is the same using the IR image with the same results as we just discussed with the visible image. We should also note that with IR images, there's an additional adjustment applied if the IR cloud tops are unusually cold. A 1/2 T-number adjustment is added. An example is shown here. Now we'll discuss T-number assignment with the shear pattern. The primary indicator of intensity is the distance of the low-level center from the edge of the deep convection. In addition to this, distinct, well-defined low-level cloud centers are indicative of slightly higher intensity, while poorly defined centers indicate a weaker intensity. Again, with the curved band, the same approach is used with both visible and IR images. Here are the T-number assignments for the shear pattern with Dvorak's original diagram. Labels have been added to the top for clarification. A comment can also be made here that the distance unit of degrees latitude is used in Dvorak's original work because grids on the old hard copy images were marked in units of degrees latitude. The distance measurement units as shown in the box with the conversion as noted may also be used and are often quite useful. This is an IR image of Tropical Storm Danielle from 2004. Note the low-level center can be seen in the gray clouds to the south-southwest of the coldest cloud tops. We can toggle back and forth between this image and the matching visible. Here's a zoomed-in picture with a 1 degree latitude grid on it, which can be used to make distance measurements to assign the T-number for the shear pattern. With this example, a satellite workstation has been used to measure the distance along the red line shown here. The red line on this diagram is 45 kilometers long and is a measurement of the center's displacement from the edge of the deep convection. 45 kilometers equals 0.41 degrees latitude. So here are the results with this example. The distance measurement of 45 kilometers gives a T 3.0 shear pattern with Tropical Storm Danielle. Now we will cover the T-number assignment for the CDO pattern. CDO is defined as the dense overcast cloud mass that covers the center. There is no eye in the satellite images with the CDO pattern. With the CDO pattern, T-number assignment procedure is different depending on whether you're using a visible or an enhanced IR image. As summarized here, with visible images, CDO size along with the extent of banding determines the T-number. Large CDOs with extensive banding indicate more intense tropical cyclones. So, two measurements are made, one for central features CF and one for banding features BF, and T-number is the sum of the two. Central feature and banding features are evaluated separately. This slide shows the CF numbers assigned according to the CDO diameter. The diameter measurement that fits most closely with these values is used. And as you can see, a determination also needs to be made whether it is a well-defined CDO or an irregular CDO. This diagram shows the assignments for banding features. As you can see, the banding feature is an add-on number with positive values up to 2. On this diagram, the upper row is for banding that averages a ½ degree latitude and width, and the bottom row is for banding that averages 1 degree latitude and width. The principle is similar to the curved band pattern. The more banding that surrounds the central features, the more intense. In addition, wide bands indicate more intensity than narrow bands. We will look at an example with Hurricane Rita from 2005. In this image, the CDO is fairly well defined and somewhat oval shaped. There is also a portion of the deep cloud on the northwest edge that could be considered part of the spiral band. Using the grid in the blue here, the average CDO diameter can be approximated to be about 1 1/4 to 1 1/2 degrees latitude. With this case, the measurement that I came up with using a satellite workstation for an average diameter is illustrated here as 140 kilometers. The 140 kilometer diameter circle in blue has been overlaid on the image. 140 kilometers equals 1 1/4 degrees latitude. The red line on this image outlines the banding features that we need to evaluate. For this example, a BF of plus 0.5 is added. So here's a summary of the results for this example. CF plus BF gives a T 3.5 intensity. 55 knots maximum wind. So at this point, Hurricane Rita in this example is still a tropical storm with 55 knot intensity. Now we'll discuss the eye pattern with a visible image. Note that it's very similar to what was just done with the CDO, but we're now introducing a new definition, embedded distance. Embedded distance is the distance of the eye from the edge of the CDO. Now we introduce the eye number and the eye adjustment factor, abbreviated here with E number and E-ADJ. So now DT is the sum of 3 values. Here are the eye number assignments given the embedded distance. Note that this measurement is similar to what was done for the CDO diameter, but now it applies to embedded distance instead and gives you the E number. Here are the rules for determining the eye adjustment factor. I'll just let you read them. But in general, well-defined circular eyes are indicators of greater intensity, while very large eyes, poorly defined eyes, or ragged eyes are indicators of weaker intensity. The banding feature measurement for the eye pattern is the same as before. Same as with the CDO pattern. Let's look at Hurricane Maria as an example. The embedded distance measurement is shown by the pink line. It is 80 kilometers, or 0.72 degrees latitude. And for this example, the eye adjustment factor is 0. The red line marks the CDO along which the eye determined the embedded distance, and the yellow outlines the banding features to evaluate. In this case, the narrow banding and the wide banding do not extend far around the CDO, so the BF is evaluated to be plus 0.5. So with Maria, we get a T number of 5.5. This is the sum of three values, 5.0 for the E number, 0 for the eye factor adjustment, and plus 0.5 for banding features. Let's now look at Rita from 2005 as another example. With this case, you can see that there's a bit of subjectivity involved in measuring the embedded distance because there is not a sharp delineation between the banding and the CDO. 1 degree latitude grid here is shown in green, the CDO region outlined in red, and the banding features in yellow. The embedded distance measurement of 60 kilometers gives an E number of 4.0. The banding features in this case are much more extensive, giving a BF of plus 1.5. Also in this case, the eye is cloud covered and poorly defined, giving an eye adjustment factor of minus 0.5. So putting together the three evaluations, we get a T number of 5.0. 4.0 E number, minus 0.5 eye adjustment factor, plus 1.5 for banding features. This example shows an eye that is completely cloud covered with rather thick cloud. Even though the eye is easily identifiable and has a very small dark spot within a cloud depression, we classify it as poorly defined or ragged in evaluation of the eye adjustment factor. Once again, you can see that considerable subjectivity is involved with this evaluation. In general, well-defined eyes have distinct inner edges, while poorly defined eyes are cloud covered. This completes our discussion of T-number assignment with visible images. And now we'll move on to deriving T-numbers from IR images. We refer to this as the EIR analysis of the Dvorak technique. This is because a specific image enhancement is used. Enhanced IR technique is an important complement to the visible technique for CDO and eye patterns. It is more objective and it's less qualitative. It also allows for Dvorak estimates during nighttime hours. Here's the list of temperature ranges with the BD enhancement curve. Abbreviations are shown, and this terminology is used for the different shades of gray. This chart shows what those shades actually look like and what their numerical values are on a scale where 0 is black and 255 is white. Now we're returning to the discussion of the Dvorak technique and the T-number assignment using enhanced IR images with a CDO. This is also called the embedded center pattern. Here, the surrounding BD curved gray shade must be determined according to the center location and a distance criteria. The coldest BD shade that the center lies within, the required distance, defines the surrounding BD curved gray shade. The embedded distance criteria that were just mentioned are shown on this chart in degrees latitude. So this is how it works. The coldest gray shade that surrounds the center by at least the embedded distance gives the CF number. Now, another important point to be made. With the EIR technique, the banding feature add-on factor determination is very different. It's completely different than what we did with the visible images. In fact, it is nearly always 0. I can refer to you to the Dvorak tech paper for more information on that, but for the purposes of this training session, we're going to assume that BF numbers for our EIR examples are all 0. And you can see the determination then becomes quite simple with embedded center pattern. With a BF number of 0, the embedded distance criteria is what determines the T number. Now, before showing some examples of the embedded center pattern, we're going to go ahead and talk about the I pattern with the EIR technique. Once again, the key is to determine the surrounding gray shade. But now it's more straightforward because you have an I. This surrounding gray shade gives you the I number as shown on this slide. With the I pattern, an important criteria for determining the I number is the narrowest width, so that the I number is given by the coldest gray shade that completely surrounds the I and is at least as wide as the narrowest width. If the narrowest width criteria is not met, you simply drop to the next warmest gray shade until it is met. On this chart, the narrowest width criteria are given in degrees latitude. Now notice at the bottom of this slide, using the EIR technique with an I, there is also an I adjustment factor. The I adjustment factor is determined by the BD curved gray shade within the I itself. The I adjustment factor is assigned by this table. Note that both the surrounding gray shade and the I gray shade must be determined to get the I adjustment factor. As you can see here, it will be somewhere between +1 and -1. So that's straightforward, but there's two additional points to be made that quickly become obvious when using this procedure. I temperature is simply the warmest gray shade of any pixel within the eye, which is an easy concept, but it can be difficult to see in the image. Another point to be made is that the surrounding ring temperature on this table is not necessarily the surrounding gray shade used to get the E number, and that's because the narrowest width criteria does not apply to the gray shades on this chart. Now we're going to look at some examples of EIR T-number determinations with both embedded center and I patterns. This will help clarify some of what we've just covered. We're going to look at a series of images with Hurricane Dennis from 2005. Here is an IR image with the BD enhancement. Here's the same image zoomed up with a 1 degree latitude grid. So what's the T number? The key determination to make is to locate the center and then apply the distance criteria. On this image, the blue circle has a radius of 1/2 degree latitude. It is centered on the subjectively located center, and it is used to evaluate the embedded distance criteria. In this case, the coldest gray shade surrounds the center by required distance of 0.4 degrees latitude is not very cold. It's the off-white shown by the patch of warmer IR temperatures just north of the center. So here's the T number for this image. The off-white gives a T of 3.5. Now let's look 6 hours later. Dennis now looks like this. Here the image is zoomed up with a grid for measuring distance. So what's the T number? With the center location shown here, the distance criteria requires that light gray be used to determine the T number. But it's quite easy to see how a different center location would give a different answer. However, the light gray is a colder shade, so the T number is higher than before. The light gray surrounding BT curved gray shade gives a T number of 4.5. And here's what the Dennis image looks like 6 hours later. Zoomed up with a grid, note the black within the white near the center. And if you look real close, you can see 1 or 2 gray pixels right near the blue grid line. So here's an example where the analyst has to make the decision or whether or not this is an eye. We can toggle back and forth between this image and another enhancement. Here's the same image with a different enhancement. So is this an eye pattern or is this a CDO pattern? We're going to look at what T number you get with either interpretation. With the CDO pattern, the distance criteria gives you a surrounding BD curved gray shade of white, which gives you a T number of 5.0. For the same image, assuming that you have an eye and that eye temperature is light gray, you get a T number of 5.5, as shown here. 5.5 is the E number, and the E adjustment with light gray gives you 0. So 5.5 with 0 gives you a 5.5 T number. Let's move on to 6 hours later. Dennis is now approaching Jamaica. Here we very clearly have a cold, well-defined CDO, but no eye. The embedded center surrounding gray shade with distance criteria of 1/2 degree latitude is white. This gives a T number of 5.0. Six hours later, Dennis's eye can now again be seen in the IR images. With this image, the eye is completely surrounded by white, and it satisfies the narrowest width criteria. The same image zoomed in, you can see the light gray eye temperature. Consulting the charts, you get these results. Surrounding gray shade with narrowest width criteria is white. the eye is light gray. This gives you eye number 6.0, eye adjustment 0, so the T number is 6.0. Now we skip ahead to Dennis in the Gulf of Mexico, clearly an intense hurricane, and there is a distinct eye. The surrounding gray shade of white exceeds the narrowest width criteria, and the eye is warm medium gray. As shown on this slide, the warm medium gray increases the eye adjustment factor to plus 1.0, so you get a T number of 7.0. This example shows that even zoomed in, the eye temperature gray shade can be difficult to determine with the BD curve. With this example, the eye temperature gray shade is off-white. This represents a range of temperatures from plus 9 to minus 30 C. With the satellite workstation, the exact warmest pixel temperature can be determined to be minus 11 Celsius. This gives plus 0.5 for the eye adjustment factor. Surrounding gray shade of white gives a T number of 6.5. Here's a black and white image of the same scene. Here's the same scene with another IR enhancement. The point to be made is that the problem of finding eye temperature is trivialized by using satellite workstation. Using the actual digital data to assign T number has also been done for many years, and that's the topic we will discuss next. The objective Dvorak technique, or ODT, evolved from the EIR technique. The idea being that images on a computer workstation, T numbers to the nearest 0.1 instead of 0.5, could be generated with a simple algorithm using a user-supplied center location. With the ODT algorithm, two temperatures, the surrounding temperature and the eye temperature, as defined here, are extracted from the digital image given a user-supplied center. This slide lists examples of T numbers assigned by the ODT and their associated surrounding temperatures and eye temperatures for various Atlantic hurricanes. Here are some results of the ODT computation plotted in time series with Hurricane Dennis. You can see that general trends are shown, but individual image results are noisy, particularly at weaker intensities. An advantage of the ODT and its assignment to the nearest 0.1 T number are the frequent image intervals allow high sampling. A time filter can be used. This plot is a running mean using 6-hour averaging period, assigning the average T number to the end time of the averaging period. This gives results as shown here using the previous data set. Reasonable intensities at T numbers above 4.5. There's also good results with the timing of the peaks and the trends. In general, this is more reliable than the absolute intensities from the individual images. This slide shows the ODT intensities from the previous slide converted to minimum sea level pressure. And this slide shows reasonably good agreement with observations obtained from aircraft for the higher intensities. This slide lists improvements that were applied to Dvorak's original formulation to come up with the ODT. This slide illustrates the problem of viewing eye temperature with very small eyes. This will cause an underestimate in intensity regardless of whether you're using the EIR technique or an objective technique. The point here is that with very small eyes and viewing angle of the satellites, measurements cannot be made to low elevations within the eye because of the viewing angle. So this is a quick review of what we've covered so far in this training. With the simplified approach of the Dvorak technique, we've covered steps 1 through 4 on this diagram. We're now going to talk briefly about assigning the CI number as indicated here as step number 5. An important aspect of the Dvorak technique is that the CI number, or current intensity number, is assigned. It is different for weakening tropical cyclones than it is for an intensifying or steady trend. The reason for this is that the T number one gets for a weakening case may at times indicate an intensity much less than the actual. This is because the cloud pattern and associated T numbers with weakening cases can decrease faster than the winds can actually spin down due to friction. There's a lot of momentum that has to be dissipated, and there's a limit to how fast that can occur. There is, however, not the same limit on how quickly the cloud pattern and its associated T number can decrease. Here are the rules for assigning a CI number. Note that the Dvorak technique imposes a 12-hour duration maximum intensity. This slide will help illustrate the CI intensity assignment rules. Here are some different scenarios showing the T number and CI number in time sequence using the rules on the previous slide. Note that accelerated weakening shows the biggest differences, but that this difference is limited to one T number. Also note that with redevelopment, the CI number and the T number once again become the same, but it is not until the T number catches up as the CI number is held constant. Another feature of the Dvorak technique is that the final T number assigned after all the analysis has been done still has some limits. These are based on observed intensity rates of change, and this was added to the Dvorak technique to assure that unreasonable intensities would not occur regardless of the reason. This concludes our discussion of the Dvorak technique, but it's important to also mention the advanced Dvorak technique, which is now being used to supplement the original Dvorak technique. A large effort beginning in the mid-90s at SIMS at University of Wisconsin is still continuing. This has resulted in automated intensity estimates with a large number of improvements, including the addition of new computational algorithms. The most important improvement over the ODT approach, which we've discussed, is that the weaker intensities can now be estimated with an automated technique. The ADT is not covered in this training, and neither are microwave techniques. In addition to the ADT, a consensus or combined approach is under development at SIMS, which combines ADT results and independent intensity estimates using algorithms that employ microwave data. To end this training session, we thought it'd be a good idea to show how well the Dvorak technique performs. The evaluation shown here was done at the National Hurricane Center. A post-analysis of track and intensity is performed at Tropical Prediction Center, and it's called the best track. For the studies shown here, the Dvorak classification errors are the difference between the operational satellite Dvorak intensities and the best track intensity. Likewise, on the right, position errors refer to satellite center fix versus best track center location differences. For both of these charts, only the time periods that aircraft observations were available are used in the study. The aircraft provide independent, more direct measurements of intensity and position. Here are some references that cover the important topics that have been discussed in this training session. This concludes the training session, and we'd like to acknowledge the contributions of Jack Bevan and Mike Turk.